So we started section 4.3 last time, and we were taking a look at, perhaps to you, a new concept called vectors. In particular, we talked about vectors having magnitude and direction, and we gave some examples about how that worked. We had some properties of vectors. A zero vector has no direction, no magnitude. Remember, magnitude means size or length, depending on the context. The negative of a vector means it has the same magnitude, but the opposite direction. And we talked about how we would add and how we would subtract vectors. And we had some properties of vectors. We also had this thing where we were taking a look at how to find magnitude. We had this whole page right here. I didn't actually give you a formula for magnitude. I'm going to do that. But it's a formula you've seen before, which is why we didn't actually need it, and we were able to find magnitude over here without the formula. So I'm going to use this slide to give you the formula for magnitude because you'll see how it plays in with what we've done. If you want the magnitude of a vector, what you do is you take the square root of the I component, like the coefficient in front of it, which is a squared, and the coefficient in front of the j component, which is b squared. And we identified last time that this is actually just the Pythagorean theorem. Okay, so it's not a new formula by any stretch of the imagination, but sometimes it's nice to sort of see it without a picture because we don't always have a picture. So if we were taking a look at just this and only asked to find the magnitude, we would simply square each of the components, coefficients, right, the 5 and the 2, and then we would have the magnitude. Okay, so we don't necessarily have to draw a picture, but it definitely goes back to the Pythagorean theorem. All right, we had taken a look at some points and finding a vector that matched between them, and then at subtracting and doing constant multipliers and subtracting vectors, and that leads us to unit vectors. Now, we had defined what unit vectors were in general last time, not even on this slide, but just what they sort of represented, but this is more descriptive. So if we have a vector and we want to find a unit vector for that vector, it means it's the same direction as the vector we're talking about, but it has a magnitude or length or a size of 1. And so the way that we find that unit vector is we take the vector itself and then we divide it by its length, right? So if the vector, for example, let's just take a look over here at this one that we had already referenced this morning, this 5i minus 2j, simply because we have the magnitude here, which makes it nice. If we wanted to find the unit vector for this, what we would do is we would take each of the component vectors, right, and we would divide it by the magnitude square root of 29. Now, we don't get to leave it that way. Y'all know that. Was it 2? It was minus. And then it was 2 over square root of 29. We're still not going to leave our radicals in the denominator, so we would clean them up just a bit. We would say 5 square root 29 over 29i and 2 square root 29 over 29j. Okay, does that make sense? So this would be the unit vector for this one, and we can kind of push them together very nicely because we've already found the magnitude on this particular one. All right, so let's do that for the example one that they give us over here on number 5. So it wants us to find a unit vector in the same direction as our vector. So what's the first thing we need to do? Find the magnitude, right? We're going to find the magnitude. And because it doesn't ask us to draw a picture, it's very nice that we've sort of thought of this from a formula now perspective for finding the magnitude. So the magnitude of vector v is going to be taking the square root, sorry, my pens are a little all over the place, the square root of each of the components squared. Now, if you really want to write -6 squared in there, feel free, but remember, we're squaring things, so we can ignore the negatives because squareds eliminate them. So you'll see me ignore them for the most part as well, but if you want to write them, you can. So what's the square of 8? 64. And what is 6 squared? 36. What happens when we add 64 and 36? This is a very nice one. It's 100. And this one actually gives us a perfect square. That doesn't always happen. So we saw the example before that didn't. This one does, and this would be 10. So if we wanted to find the unit vector of this vector, which is what we're asked to do, we would divide each of our components, in this case, by 10. Now, we don't have to rationalize, but what do we have to do? Simplify, right? So we're going to simplify whatever that looks like here. It doesn't include rationalization, but 8 and 10 both have something in common. So what will 8 over 10 reduce to? Y'all are scaring me a little bit this morning. 4 over 5, thank you so much. 4 over 5i. And what will 6 over 10 reduce to? Yeah, 3 over 5j. It's possible that my math lab might accept the answer if you give it in a non-reduced form. I'm not exactly sure, but I'll take points off if you don't, because I think that that kind of simplification is certainly within a realm of something that we should be working with. All right, any questions on this last component with unit vectors? All good. Okay.